Hello and welcome to Sean White's Solar and Energy Storage Podcast. Today we have a good friend of mine, Paul Subzak. I think we met last year, so he was my favorite new person of 2023, and we're in 2024 right now, but you might be listening to this in 2030 because it's so important, it's timeless. Say hi, Paul.
Hello.
And Paul works with giant utility scale solar projects. He probably doesn't even know how to size a wire for something as small as a house. And speaking of houses, we are at my house where I live in Orinda, California right now. And I thought it might be appropriate to do an in-person podcast with the other person sitting right next to me, because recently I've had people as far away as Ike Weber in Germany, Andy Klump in Southeast Asia, and now we are recording like within touching distance. There, we just like high five.
High five.
Ooh, high five. That's my favorite movie, High Five from Borat. So we're going to have a little bit of fun today and talk about some of these big projects. And I imagine, too, that with some of these big projects, some of it's kind of secret, right? Like you've got NDAs and all that kind of stuff, too. So we're going to try to get all the secrets that we can out of Paul, and I'm going to trick him a little bit. So in my last podcast, I was talking to somebody that was doing projects that were up to 20 megawatts. In fact, he was even calling it distributed generation, DG, for up to 20 megawatts. And if you go back, 20 megawatts was the biggest job in the world at one point in our lifetimes. And so it's kind of crazy how much bigger these systems are. And so for you, Paul Subzak, 20 megawatts, what do you think about that size?
I'll build some 20 megawatt projects. I was just out at 14 megawatt DC project in Michigan last month. So I'm still currently building those. But scale that I would like to build is 300 to about 800 megawatts.
So 300 to 800. So you do a little bit of this little small time sub 20 megawatt stuff in your spare time?
Yeah, there's a distinction with a lot of the utilities, and the term for distributed generation is kind of into the, not the transmission grid. So just like the normal grid, you can go with a recloser and tie in there. Usually it's a small grid interconnect application that's a lot easier. You don't have to go through months of interconnection study with the utility.
Maybe we could define some of these things. Yeah. So you said recloser, and you were talking about big grid and small grid.
Yeah. So transmission lines are like 69 kV.
So kV is kilovolts.
Right.
So that's like the voltage, that's the electrical pressure. And so you said 69 kV. Why 69? Is that just your favorite number?
They've just chosen different steps. So 69 kV, 115 kV, 230 kV. These are for long distance.
You're not going to tell me 420 kV now, are you?
I'm not aware of it right now. Past 230, there might be another step, and then they start to go into high voltage DC. So the losses start to make sense.
Cool. Are you working with any high voltage DC right now?
There's very little going in.
So you just put
US.
like 10,000 modules in series and you got high voltage DC?
No,
we're just kidding. It doesn't really work like that. So Paul, what would happen if you put 10,000 PV modules in one PV source circuit? That's one string, like 10,000 modules in series, like a couple of megawatts. What do you think might happen? You would have the current, when stuff's in series, the current doesn't go up with series connections, but the voltage would be kind of crazy high. Maybe it would just start like arcing. Maybe it would start going through the ground, maybe?
Yeah, probably something like that because of the way the components are built. So as you build up potential energy, it wants to go the path to...
Maybe we could do an experiment. Like on your next job, just kind of design it wrong and then just see what happens.
Just hook it up.
Yeah.
It would be very easy to hook up 75 panels or 150 panels in series because they're all right there and they're,
And so are all the projects that you're working on 1500 volts DC?
Yeah.
Yeah, and so that's like the top end of the code, 1500 volts. And have you heard any rumors? I do hear some rumors about someday they're going to go higher.
Yeah, I've heard rumors from a leading IPP, which is independent power producer that owns a lot of solar assets that they're trying to push up to 2000. It comes with all this change And I don't know if it will happen or not.
Yeah, because that would be outside of the NEC, but then when you're utility scale, you can do things that are outside of the NEC pretty much.
Right, but engineers are pretty hesitant to go outside of the NEC because at every location that we install, there's an AHJ, which is the authority having jurisdiction that knows the NEC, and they have the authority to shut down site and make things installed to code. So that's kind of a dance. In the substation world, all of the substations are under the NESC, which is
National Electrical Safety Code.
Yep.
So do you have the National Electrical Safety Code memorized?
I have neither of them memorized, but I
You mean you have to look at the book? You don't have a photographic memory?
Yeah, of course. It's just, it's 350 pages of dense technical information from everything from transmission lines to the spacing of buses at a substation.
So you were talking about like different voltage interconnections, and what was that, like a study or something like interconnection?
So there's like two different levels of interconnection. There's the small grid interconnect.
And so what do you mean by small grid?
Small grid is defined differently in different utilities, but for a general rule of thumb, 20 megawatts and below.
So when you connect to 20 megawatts, that's considered small grid?
You have to do an application with the utility.
The grid has probably got more than 20 megawatts on it from other sources, but you're just talking about when you say that it's the small grid is something around...
Small grid is distribution grid.
Distribution grid, okay.
That brings power to this neighborhood.
So not the transmission grid, like those big power lines that are going from one city to the next.
Right, from power plant to power plant, you're going to have transmission lines. And
so what kind of voltage are you seeing on like the transmission versus the distribution?
Distribution grid, I think, is 12.7 is pretty common.
Pretty common. So 12.7 thousand volts or 12.7 kilovolts.
kV.
Yeah. And so that might be what's close to where we are here in Orinda, California.
Yeah. Yeah, I don't live on the distribution grid very often, so a project that I have is at 25 kV is what they're interconnecting at. And
so that would not be the small grid?
That's small. Yeah.
Okay.
Once you're over 100, you could say that's transmission.
Once you're over 100 kilovolts, then that's more like transmission.
Yeah.
Okay.
So that's the distinction. Distributed generation is happening quite a bit. Community solar would fit in this.
So you would say like distributed generation is more like on the distribution grid?
Yep.
And then you would say that if it's on the transmission grid, then what would you call it?
Utility scale.
Utility scale or...
Right. And if you're doing DG, you're at lower voltages and you can use a specialized switch gear that has started to crop up in the solar industry. There's one company that has a big market share called Clear Sky. You could have one of those at your site, or you could use a Recloser, which is a piece of electrical equipment that can open and close.
Yeah, so it's sort of like overcurrent protection in a way, for an analogy.
Yeah, the reason they call it a Recloser is because it has an automated capacity to close 3 times. So, and the reason they have that is if a tree falls into an electrical line, they can often shock it and have it bounce off. So they have programmed usually 3 steps of reclosing to help.
Yeah, and sometimes I think of that as like, let's say you're up in the mountains somewhere and a tree falls down, and then your lights, as they go out, they kind of blink, and sometimes they stay on, and sometimes they don't stay on, but they kind of give it a couple of chances.
Yep, 3 chances, and then it goes off.
Yep, every time some guy up in the hills drives their truck into the power pole because they had too much Coors or something like that, you know?
Yep.
Maybe that's what's happening out there. So that's why they have those reclosers for those guys.
I mean, if you hit a pole and it loosens so that the conductor is going to fall and sag, you're going to have a bigger problem.
Maybe we should have recloser circuit breakers where it gives you like 3 chances. And it kind of reminds me a little bit too of just inverter specs, like you have things like low voltage ride through and stuff like that. So as the grid gets more and more solar on it, we have to have our inverters not all turn off at once, and it's sort of like giving it an extra chance to stay on so you don't create some kind of chain reaction disaster of having everything turn off all at once.
Yeah, cause a big brownout.
Yep, brownouts. Don't like those. I remember like studying a long time ago about some of these brownouts of the century or something where they, one place has a problem, maybe even a squirrel gets electrocuted, and then one thing leads to another, and then half the country's without power. And I don't think that's happened in a long time. Do you remember when?
There's been a few rolling brownouts have happened on the East Coast, and Texas has had quite a bit of difficulty with reliability of the grid down there that I think would fall in that bucket.
Yeah, I remember like studying in history class or something a long time ago, like the great electric problem of the 1970s or something like that. I can't exactly remember, but but bad things can happen, and you don't want everything to go off all at once. And that's why we're getting really smart with our inverters. And at first, when solar is just like this little fraction of a percent of the grid, which it's not anymore, but it was when we started, it doesn't matter if all the solar turns off all at once. And that was done for safety. And now we want things to be more grid forming like.
Right.
So we have grid following inverters that turn off real easy. They're kind of sensitive to turning off, doing anti-islanding. And then grid forming inverters where they're more likely to stay on for different reasons.
Yeah. In my world, I'm always grid following. And the size of my inverters are around 3 megawatt on a skid. So we'll have like a platform, it will arrive on a truck.
Can I put that on my roof, 3 megawatts?
No.
It's not like an in-phase inverter or something?
You would need to reinforce the roof. You could put it in one of your bedrooms, and it would be the main feature.
So like a 3 megawatt inverter.
3 to 4 is
3 to 4 megawatts
right
is pretty common. And why is that a common size? Does that have to do with the transformers or?
I think it more has to do with the amount of inverters you can fit on a skid and shipping it in a compact.
Do you put those together in groups, like multiple skids in the same place, or do you stick them in different areas?
Generally, no. We'll do a whole block, and there'll be one inverter in that block. So if you had a perfect utility scale project, it would be a giant square, and every block would have an inverter next to the road, and you would do it like that.
Cool.
So on the smaller scale stuff that's rooftop, the grid forming inverters, when did those start to pop up, and what's the use case?
Yeah, so the way that I've learned it is that grid forming is kind of a new thing, and we need to have that in certain areas where there's a whole lot of solar. And so it's getting to be important in places like Australia and islands and things like that. But just the greater penetration of solar, we're going to see more and more grid forming inverters. And so we don't really see too much of that in practice right now in a lot of places. But when you buy an inverter, they're starting to make them so they're more likely to have more grid forming characteristics. And so one of the things that happens is you have all this spinning stuff with inertia on the grid, like coal plants and nuclear power plants, and there's like big, heavy things that are spinning. They call that spinning reserves. And the one thing about an inverter-based resource, IBR, sometimes people call it, is with the inverter-based grid, is that with solar and an inverter, you can't really have much in the way of grid forming because it's not like you're just going to all of a sudden triple your output because you're already working at full power. But when you hook it up to energy storage, then you can do things like that and give little pulses of extra electricity to keep the grid running smoothly rather than turning off all at once if there's some sort of an event.
Yeah, and then I think you can do things to help frequency regulation with grid forming and inverter technology,
Yeah, and so frequency regulation, that's when the frequency of the grid slows down, and then you inject more power into the grid, which makes the frequency go up. And we have a 60 hertz grid in the US, a lot of places have 50 hertz. And if the grid is going too fast, you could put less power into the grid, or even time to charge your batteries. And sometimes it could just be a second here of charging, and then the next second you're discharging, things like that.
Yeah, I heard on commercial airplanes, the grid or the electrical system there is at 400 hertz.
I think I've seen that on a sticker on an airplane. I was like, what the heck is that?
400 hertz.
You know what I should do is sometimes I travel with this little, they call it a kill a watt, like you're killing watts, and it tells you the frequency and stuff like that. I should plug it into the plane,
Well, where would you plug it in?
just like at my seat.
I think that's got to have a
different inverter or something like that?
Yeah.
Oh, okay. And so maybe that has something to do with the rotation of a jet engine when you're flying? Maybe it's going at like 400 cycles per second or something like that?
Or something in the early days that caused the interference at 60 hertz and they wanted to change.
Wow. Okay.
I'm not sure. don't know.
Okay. Well, it's like next time I'm on an airplane or next time anybody listening's on an airplane, bring out your meters and start measuring frequency and see what the flight attendants and the pilot do when you where's the engine room?
I think you need solar or airplane mechanic on a future episode and get to the bottom of it.
Yeah, I have a friend that's a 787 pilot. Maybe he could get into it with us a little bit.
Solar airplanes, I don't think exist yet.
Well, they do have that Solar Impulse, the one that's flown around the world, that's got a wingspan a little bit bigger than a 747. And there's these two guys that go around talking about it, and they've actually gone around the world in this thing.
It's unmanned, like a drone?
No, two guys sitting in it. Like they take turns. They flew it. I think the farthest was across the Pacific Ocean, and they went from Japan to California, I think it was.
How do they take off?
It does have a battery in it, or multiple battery cells, and they just take off.
Or maybe they get towed.
No, they just take off, and then they go up high, and at night they lose altitude, and that's sort of like energy storage. Yep, the Solar Impulse, pretty cool thing. So anyway, we're talking about like big, huge stuff. And I know that there's a lot of talk too about using string inverters for large PV projects and benefits and drawbacks to that. Are you mostly sticking with the big central inverters? And
big central is 99% of what I see. There is some talk of doing string level.
And maybe that's because of the company that you're working with, that's their choice? Or
I'm not sure where the trade-offs come in. For a little while, there was some problems with supply chain, and it could have stemmed from that. Or maybe there's better economics on the smaller inverters, and so you could scale it up.
Yeah, there's all kinds of benefits and drawbacks. So let's see, they say for the string inverter benefits, you don't need DC balance of systems like combiner boxes and all that kind of stuff. You just put the string inverter where the combiner would be. You've got maximum power point tracking that's usually 2 strings per MPP. And then if something breaks, it's easier to replace. But then I sort of look at it too like the micro inverter versus string inverter. But then now string inverter's on the opposite side. And so when the string inverter's the bigger inverter, also you say there's less stuff to break. So if you have a whole bunch of string inverters versus a 3 megawatt or a 4 megawatt inverter, you're going to have less inverters breaking down,
right?
Because there are just less of them. And I believe like the big driving thing behind using central inverters is price per watt. They're less expensive per watt and all that kind of stuff.
Yeah, is the economics of the projects that we all build. Yeah, whichever's cheaper, that's what we'll build.
So some of your bigger projects, what's an example of like how many of these giant inverters that you use?
It can be 7. I have a project with 68, another one with 72.
72 inverters that are like 3 or 4 megawatts?
Yeah.
Wow,
it's a lot.
Big. That's some big stuff. And when you're doing these big projects that are these hundreds of megawatts, what does it cost just for your wire?
So the biggest, we can outline the different wire. There's the wire that's on the ends of the panels that has MC4 connectors on it. And then we'll plug in harness wire into that. And that will go to a combiner box or a load break disconnect. And from there, it will go into a larger DC cable. Sometimes there's a connection that goes directly to that larger DC cable. And the trade name for that is called a trunk bus. And then from there, it will go into an inverter. And out of the inverter, it goes from DC to AC. So then I have medium voltage cable, which is giant. For the people that can see, I'm holding my hands up and it's
inches across.
Yeah, it could be inches across, 4, 5, 6 inches across.
So Bill Brooks, who's been on this podcast more than anybody, that's also on a lot of my classes that I teach with, he came up with the idea for the trunk bus. And so what a trunk bus is instead of using a combiner box, you're just using a big cable that you just hook up all your circuits to. And so they'll be in these different harnesses that go to this trunk bus.
Right.
And sometimes they're with IPCs, insulation piercing connectors.
Right.
Or sometimes just built into the trunk bus will be the branches off of it.
Overmolded design from the factory. So and I'll do both. There's a few options that are using the overmolded design, and it will kind of have an octopus of cable that will come out. So it could have between 4 and 8 MC4 connectors that can get plugged in at different locations.
I'd hate to be like the 4-tentacled octopus.
Yeah. What would it be? Quadrupus.
Yeah.
Yeah, and then the insulation piercing connectors, there's a company called TE Connectivity, that came out with a solution about 2021 when they were doing their first commercial installations, where you field fit where you want that to go, and then you would tighten down this bolt that would pierce through the PV cable into the conductor there. One version that they went out with, and they came out, I think, at last year's RE Plus, a new upgraded version that is better reliability and has gone through a battery of tests. And then there's a few others that are maybe not on the market yet. But it's pretty cool because you can field fit it. The downside to that is you have to have people out in the field doing that work in an environment that can be very variable, and dust can fly up and all these things that you can't control for.
So copper or aluminum?
Almost all of the PV that I do, almost all the conductor on the utility scale is aluminum, just because of cost reasons. And the majority of grounding that I do is copper because of NEC.
So the harnesses even that you're connecting to the PV modules themselves?
Those are generally copper until you get to the trunk bus. It's possible to do those in aluminum. You have to have a dissimilar metal connection, but right now it's not that common.
And then inside the harness, like I know residential solar installers, they're always using number 10 wire. What do you use? I know that when you do the calculation a lot of times, you can use a small, even a 14 gauge wire a lot of times.
I'm number 10 and number 8 is where the
So
harnesses
even for
is.
like individual modules? you
Yeah,
get-
so the size of the panels that I'm working on are 450, 550, 650.
So those are watts.
Yeah,
450 to 650 watts. They
And-
sure are getting bigger.
For one string, it will be 20 to 27 panels per string, and those will all come back to a trunk bus.
And so I know that the National Electrical Code, when you're over 100 kilowatts AC, they let you do things under engineering supervision, such as put more modules in series, as long as you've used your engineering knowledge, and they talk about a certain Sandia study for advice on that.
Right.
So you're one of the engineers that's supervising this kind of stuff.
Right. And then they're permitted through the local jurisdiction, and they'll be stamped with a professional engineering stamp.
Do you run into problems sometimes? Like you go into some podunk town that's out in the boondocks and you're trying to install a $1 billion solar system, and then Joe, the inspector, comes out and he's like, I think you need another ground rod or something like that. Do you run into that kind of stuff?
Yeah, but to kind of fall back on like the podunk part, we build in rural areas, but we generally are pretty strong in that community. So, and a lot of the people that
You just like
That-
somebody
that I
pays
have-
off the politician?
No, a lot of the people that I have built are from similar communities or from that same community. So we have a really strong connection with the community that we build in, and we'll buy meat from the local butcher and all this kind of stuff.
So that does sound kind of like politics, like, shaking hands with the local butcher.
Yeah, you have to. You have to be proactive when you're in a community and you're bringing all these construction vehicles in. You gotta
And lots of jobs.
lots of jobs and traffic, and you have to be a steward of the land that you're improving. And I did a lot in my early career in the wind world, and we would build 300-foot towers and deal with the same AHJs, inspectors. But these electrical components are huge, and there wasn't very much interest. Once we got to solar, all of the inspectors would maybe put solar on their house. So early days, all the inspectors, they wanted to know everything, so that it was kind of a learning experience for them, and some of those circumstances could get more involved, more questions than I was used to.
There's wild animals.
Squirrel.
There's a
So-
bobcat that walks right across this table sometimes. But yeah, sorry for interrupting. I was trying to get into the podunk vibe with the wildlife and all that kind of stuff.
Yeah, like every region of the country is unique, and we deal with everything from labor relations, working with unions, working with apprenticeship programs, working with journeymen, master electricians in different parts of the country, and do a lot to do things right the first time. So there's always enough time to do it again. Never enough time to do it right, always enough time to do it again. So we like to do it right the first time and get it done and move on to the next one. So.
Cool. So you deal with all the political stuff, buying butcher meat in the right jurisdiction, and I'm sure it's vegan meat, don't want to offend anybody.
I don't think it's vegan meat, Sean.
So you're doing that, but your main job is engineering these systems. I wonder, as far as like copper and aluminum and those metals and things like that, I remember one time you were like, I just ordered a $50,000 roll or something. I think it was something like that. So for one of those big projects, how much money goes into the wires, do you think? Just if you just had to throw an order of magnitude at it.
Let's say 100 megawatt project. The biggest expense is inverters, panels, and pile in the tracking system. And then the wire comes in after. So 100 megawatt project, you're probably looking at $1 to $2 million.
$1 million to $2 million worth of copper and aluminum.
Copper and aluminum, yeah.
Okay, all right.
DC and AC wire.
I bet you probably get a bulk discount.
You operate in different types of things. In the solar world, in the wind world, you operate directly with the cable manufacturers for the best price. With the advent of wind, the first medium voltage cable, 35 kV, this is what connects the underground system, the underground AC. That runs at 35 kV, and the first cable that was being installed in the US there's this guy Bruce out in Palm Springs, California, that was ordering a lot of cable from General Cable because they made it. And they like, what are you doing with all of this cable? You're not a utility, you're not a normal player, like what's going on? Let's do a partnership deal. So he became a dealer for General Cable that for a long time had the whole marketplace. And then about 5 years ago, some companies have invested in factories to build cable stateside, which is starting to become a bigger play, especially after the IRA, where domestic content is king.
Yeah. That's a lot of millions of dollars worth of cables and copper and aluminum that you've been speccing out.
Yeah. I've also designed circuit boards, and for those that work on circuit boards, you can have a little credit card size board, and that's your circuit. On one of the wind farms that I was at, I calculated that the total size of my circuit board there's 54 miles of underground cable that I had at that one project.
54 miles, wow. That's pretty impressive. And I guess we're not going to run out of aluminum. There's plenty of it, right?
Aluminum shortages, I don't believe, are forecast. The price of copper currently, right now, is close to peaking. And the last time it peaked was around the pandemic. So prices are going up again.
We interrupt you for a very important announcement. Sean White's Solar and Energy Storage Podcast has been brought to you by Sean White's Solar and Energy Storage Podcast. That's right, Sean White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSean, that's solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show. I think it's probably interesting to a lot of people that it's mostly aluminum that you're using. So as far as there being a copper shortage that's going to limit you, it's aluminum. Yeah. And so the difference between copper and aluminum is per weight, aluminum actually carries more current, but per size, copper carries more current. Copper is better than gold at carrying current, not quite as good as silver, but very close. And then, next up comes aluminum, and aluminum oxidizes, and aluminum oxide, when aluminum reacts with oxygen, it would just be on the coating of the wire, is not good at carrying current. So you just prep it right. You just have the right connectors, you put a little sandpaper on there, a little emery cloth, a little antioxidant, and it works great. There's utilities love aluminum. Those wires that you see up there are not copper that are going across. And then another benefit of aluminum too is it melts easier. So if there is a problem, it opens the circuit.
One caveat with grounding is aluminum is not allowed for grounding that goes in the ground. Because of the corrosive properties. It will. There's one kind of solution that sometimes people will use is copper-clad steel for grounding in place of pure copper.
So let's explain what that means, copper-clad steel.
Right. So you have a steel core, and then you would coat copper around it.
And so the copper holds up like the Statue of Liberty. And so let's maybe talk a little bit about some of the other things. So they say that somewhere around 2/3 of the solar in the United States is utility scale, and more would be the rest of the world. And a lot of people think of solar as being residential or commercial because they see rooftops all the
Right.
time. But it's the big stuff is where most of the solar is going. And are most of the projects that you're working with, or all of the projects you're working with, single axis trackers with bifacial PV? Is that pretty much what you're dealing with?
Single axis trackers have taken the market, and bifacial kind of crept up because of some trade embargo, and it's just stayed. So
Yeah, I think that maybe the tariffs, bifacial PV's been exempt from tariffs, or it's gone back and forth.
yeah, but it came out of nowhere, and you put the cells on both sides. So
Yeah.
there's some projects that have put reflective white surface on the base of the ground, so you can get a little bit more bifacial gain. But generally on utility scale, you're not going to paint the whole ground white. You're going to have vegetation there.
Well, if they do the agrivoltaics and then they get some sheep and they have white wool, that
Yeah.
kind of would reflect it a little bit, get you
Yeah.
a couple bucks after that. And I've noticed too that even if you go international, bifacial single axis trackers is really popular. So it's not all about the exemption from tariffs.
No, I think that's what prompted it to grow, and then the falling cost of modules. It doesn't cost very
And
much to
what
have
do you see for the price of modules?
It's currently at a floor right now. It's at about 12 or 10 cents.
Wow. In the
10
United
cents
States?
a watt, not in the United States. That's global. Once
all
you
that,
get to the United States, it's bottoming out at about 30 cents a watt.
So that's like triple almost.
Yeah.
So why would you think that it's triple the price? Even though like being triple is still cheap historically and all that, 30 cents a watt is pretty cheap. But is that because it's bifacials more expensive,
No.
or you're using higher quality
Same
stuff?
product outside without, it's the tariffs.
It's the tariffs. But the bifacial is supposed to be exempt from tariffs right now. That might be changing.
Bifacial at one point was a way around some tariffs. So, like, however,
Okay.
the legislature was written did not include this
Yeah.
bifacial thing. So then they were like, well, we'll just sell bifacial panels.
Yeah, and that's always changing, and this is pre-recorded, so by the time that you listen to it, it might change again, maybe 3 times back and forth. There's
Trifacial.
Trifacial.
They got cells
Yeah.
on the edges.
Yeah, it's funny that you mentioned that. I have a friend, Nico Yuen, and he's a German guy. And we went to the solar conference in Munich, and this is probably like 5 years ago. And he took a year off, and people are like, where have you been? And he was like, well, I'm working with this new company, and we do trifacial solar, and it's so efficient, it works indoors. And about 10% of the people believed him. And so that's like a good gullibility test. If you tell them that you got trifacial solar that works indoors, but we were talking about octopus cables, so we have octofacial.
The latest is doing tandem, taking 2 different PV technologies and sandwiching them together, that they're better at different things. The price point is significantly higher, but that's like the next phase of PV, is putting 2 different technologies
And
together.
they've even done that a long time ago. I think even like 20 years ago, there was like Sanyo, they called it HIT, heterojunction technology. I think they were using crystalline silicon and amorphous silicon for multiple layers of stuff. And they had bifacial and stuff too. But that stuff was expensive. It was probably well over $5 a watt.
And HAT is starting to come into the market. A lot of this is the innovation exists, but a factory has to have a clear line of sight to profitability before they can pop up, because the whole solar industry needs to make money. So you need 3 to 5 years to pay back on your capital expense for your factory. So you need to know that you could beat out the cost curve of dropping prices.
Yeah, you don't want to invest billions of dollars into your assembly lines. They call them manufacturing lines
Right.
for the solar module, and then go like, oh, we're going to switch out that manufacturing line that we put up last year because we're going to make some kind of new tricky technology.
Right. There's a lot of teams and domestic companies that are interested in manufacturing in the United States, but we have this regulatory uncertainty of what's going to happen when we change a presidency, if they'll roll back some of the latest legislation like the IRA, or if that will continue. The uncertainty causes people to not want to invest capital.
Yeah, and
'Cause if
uncertainty is bad for business. Yeah.
Uncertainty is bad for business. Having a line of sight for the next 5 years where you know that you can make some money is good. Interesting, there's a lot of foreign companies that are coming in and building solar panel manufacturing right now. Q-Cells has probably the biggest plant down in Georgia that is starting to come up to operation.
Have you been down there? Have you seen the
Yeah, I know somebody, and I asked if I could get a tour, and they said, I can't even get a tour.
top
So,
secret? Yeah. And we're going to do a class together. We're figuring out when we're going to get together and make a class.
Right.
And we're going to talk about a lot of this stuff, and I'm going to post it on solarshawn.com and put on HeatSpring. And you people that are watching this podcast should take that class. It's a little bit early right now. We're just kind of in the beginner stages of this.
Right. We'll for sure include some site visits, and we'll go to some of these utility scale projects and hold the conductor and the DC cable in our hands and, talk about it. Maybe do a medium voltage splice through all the steps and use like a giant crimping machine, and you got to do the right amount of crimps and prepare the cable, and there's semicon and insulation and all these different aspects of these.
Yeah, and then we're going to plug 2.5 megawatts of PV in series and 1 series string just to see what happens.
Maybe you can figure out a way that we can do that, but the project owners for the projects I work on would not be happy about that.
Yeah, I know. We better not tell them, huh? Yeah, and of course, we're just joking around, so don't use this against us. We're not telling you to do things that would cause serious problems besides just being OSHA violations.
Follow the directions.
Don't do the lick test on a megawatt, nothing like that.
Earlier, I was speaking about medium voltage cable and going underground. There was one project that I heard of that was in development that was using 69 kV cable underground for the same reason as you would with transmission lines. The higher voltage you go, the lower your losses are. But I've never put my hands on it, the 69 kV underground. So.
Yeah, and we were recently talking about, I had a student that had a question, and it was about derating cable when it's buried. What kind of temperature do you use for that? And so I asked Paul, and he's like, well, we just use this $70,000 software.
Probably somewhere around
So
there,
that's called engineering supervision. Do you want to talk about that software?
Yeah, so there's a few softwares that you can use to...
And is that like $70,000 a year?
The actual cost depends on like how many modules and how many seats that you'll have. It's an enterprise software package, and I think it might be closer to $35,000-$40,000. The leading software for cable ampacity studies is called CYME, CYME. CAP. That software was acquired by Eaton, that company, about 5 years ago, maybe now.
And so that would be like, it's not just for renewable energy, I imagine. It's
No,
probably
it's
for
for
utilities.
utilities. Yeah, you can do duct banks, you can do direct bury, you can do cable and conduit, all sorts of underground applications. And the input of that program is the specific characteristics of your cable, the amount of insulation, like every aspect of it, how many conductors, how it's compressed, or
So this is what we call
different
engineering supervision stuff. You're not going to use this on your house.
There's engineers that do probably, but yeah, that program is pretty involved. But with every iteration that you do, you can hone in on the specific soil characteristics of a job site. You'll go out, you'll take a sample of the soil, and then you'll put it through a thermal resistivity test.
So you got soil samples going along with this? Wow.
Yeah. Soil samples that will measure the electrical resistivity on one axis, and the other axis will be moisture. Moisture is usually on the x-axis and resistivity there. So as cables dry out, or as the soil dries out, the resistivity of the soil goes up and the ampacity goes down. And there's a whole...
So are you like looking at leakage currents and things like that for... Is that why you're worried about the resistance of the soil?
The reason we care about it is because we'll run the cables at 90 degrees
That's
C.
the rating of the insulation.
Yeah, when I'm coming into a substation, I want my cables to be around 90 degrees C to maximize them. They can take that
That's
much.
pretty typical with residential solar, is 90 C rated insulation. So,
And then I have different soil characteristics. So coming in, I need to take into account the soil at the substation, whatever that test showed, and then the amount of parallel feeders, and the proximity of how close they are. So if I have 10 parallel feeders...
And you're talking AC, alternating current.
Yeah.
And then,
they'll mutually heat. And the soil, when it gets heated up to 90 degrees C right around the cable, it starts to dry out. So we do either a 3-part model of the soil or a 2-part model of the soil that kind of makes a dry out box. It says the cable in this box around the conductor will be dried out, 0% moisture for the life of the project, and then the rest will be at native.
So when you're running the software, you're trying to calculate how to get it not past 90 degrees C for a 90 C rated cable?
Right.
And so that's kind of what you're looking at, which is a lot different than the way that we do it for like residential commercial, the National Electrical Code without engineering supervision. And we look at the ambient temperatures and things like that, the expected 2% high ambient temperature that you could get from the Solar ABC's website if you want. I go through that in the classes and things like that. And so when I was talking to Bill Brooks about this recently too, I was thinking too that you probably, like if you're just burying cable in your backyard, you probably don't need to use those higher temperatures because it's cooler when it's buried underground. And so probably 30 degrees C works just fine. And what that pretty much means is you don't need to use any ambient temperature correction factor. Yeah, if you're burying it. But I think also too, if you look in the table for ambient temperature correction factors, if you go down colder, you can actually carry more current. So if you're up there, for all of our listeners that are in Greenland right now, you could carry more current than what it says in the tables, because you have, like, instead of a derating factor, you would have what I could call a super rating factor.
Yep.
Super rating. Super.
A multiplier above 1, which is shown in the tables.
That's pretty cool. And I'd start naming the tables, but they keep changing the name in different versions of the code. And I just make
formerly known as the Prince table.
Yeah.
I looked at this table that Sean's referencing, and I saw the super ratings, and it just doesn't feel right. So I had to look again, and it was for the colder temperatures. You can get more ampacity through the cable.
And I know that working with some people, it's been a while, that they were doing this geothermal heat pumps. There was this company called Canadian Geo and Solar, and I was consulting for them 15 years ago. And they were telling me that I think it was like when you go 6 feet down, something like that, the temperature down there is just like your annual average temperature. Like it just like summer, winter, doesn't matter, just the same temperature.
It's like a cave temperature of like 40 degrees Fahrenheit.
Yeah, I recommend everybody go to a cave near the site you're going to do work on and just measure the temperature.
Yeah. Exactly. I do that every time.
Yeah. When I was a teenager, I was actually a real gold miner. So the price of gold shot up in the 80s, and my dad had a rock quarry, and they brought me some soil from this old, it was called the Jupiter Mine. You can actually read about it in the California history books. And I made an ounce of gold that summer, which is not bad for like a 14-year-old.
How much money do you remember?
I think it's like $800.
Pretty good summer job.
For like a 14-year-old in the early 80s, something like that, not bad at all.
And how did you collect it? Like, how did you get that?
I just sold it to my dad.
No, how was the gold?
Like? So they brought up a dump truck load that was from the front of this old mine.
Yep.
And inside of that shaft, we could go in there, and it was like that temperature that was constant. And they brought me a dump truck load by the double wide mobile home. And then I had a rocker box and a hose and a pan. I'd take some shovels of dirt and I'd put it in the top of this rocker box. I'd spray water on it, and then, the gold's heavier and the gravity brings it down, and I rock it back and forth. And then I would pull out, after I put enough dirt where I would start seeing gold, then I would take out the pan that had like some grooves in it where the gold would settle. And then I would dump that into like a gold pan. And then I would just do that thing, the gold panning, and have like these different colors of, some of them were plastic, some were metal and things like that. And you just swirl it around, and you end up with this combination of black sand and gold. And then you can just pick it up with your pinky and put it in the little vial, and they stick it on a triple beam scale and pay me a date for a day's work or a week's work or whatever it was. And so, it was like a real gold miner, if you can believe that.
I can believe it.
It was a place called Angels Camp.
What part of the country?
It's California. It's sort of like east of Stockton, hour east of Stockton.
I think the biggest operations are strip mining, where they kind of process huge amounts of earth to get gold right now.
Yeah, like actually where we were, they did some placer mining where they just take high pressure water, and they did this like in, I guess around like, 1850, whatever, gold rush. Right. And they washed out like half of a mountain. Yeah. And then we had all these swallows that would come there, and there was a tunnel that went back into the mountain that we opened up, that we found and went into it, which was kind of, very non-OSHA probably. It's like bring your 14-year-old son into the earth. But it was kind of weird. Like you could see like the stuff that people were doing over 100 years earlier, and they had like their timbers in there, and like there's an old wheelbarrow, and I remember like some of these geologists were coming in there and finding little red rubies and stuff like that.
Oh, nice.
That's pretty cool. Like little small ones that weren't worth a lot. But then back in the time, then the price of gold went back down, and I was the only one that made the money. So they were thinking too big. You know, I was thinking like $800 scale, and they were probably trying to think $800,000 scale.
Utility scale gold mining.
Yeah. But yeah, so let's maybe think about, I mean, we've been going at it for a little while now. What else would you like to talk about? Or we could also have it to be continued for another time too.
One aspect that is worth, if we're focusing on scale and bigness, there's a project that I was a part of that ended up being 820 megawatts DC.
Where was that?
Outside of Houston in Texas. So
Yeehaw.
just
I'm heading there in a couple days.
to Houston.
Yeah.
Houston's got a lot that's happening in renewables, and out there they don't say climate tech, they say energy transition, and it's all the
It's cool.
oil majors are out there.
I don't care what they want to call it.
Yeah.
As long, you know, it's like whatever they're doing. If they like calling it an energy transition, then they're doing it. They're transitioning the energy. They're becoming
Right.
less dependent on foreign oil. And if they go to San Francisco and they want to call it climate tech, then those people that are doing energy transition, they don't call it climate tech. They're still doing the climate thing.
Yeah, we got to
even
do
though they
the-
don't know it.
We
Yeah.
got to do the political thing in America. So.
Hey, it all works. Like we're all on the same team.
Yeah.
If we want to call it different for different reasons, I don't think that's what we need to focus on.
Yeah, I think we're in a shift where most of the energy up until recently has been from fossils, and then we're shifting to wind and solar, and it's a better energy source in a lot of aspects, and not as good in other aspects. But there's the levelized cost of energy for solar has undercut new coal plants for a significant amount of time, like the last decade or so, and all the energy companies they're like, we want to be an energy company. We don't necessarily want to be just an oil and gas company because we can see the end of it. So they're transitioning to these different energy sources.
And there's probably like more money to be made with renewables. Renewable energy is less expensive now. And it used to be 10 times more expensive,
Right.
and now it's less expensive. And one of the things too that I've heard of people looking at is right now it doesn't make sense to make a new coal plant. But does it make sense to keep a coal plant going that's already working? And then you get to the point where solar and wind are so cheap that it doesn't even make sense to keep it going.
Yeah, I mean,
And we're just talking financial sense. We're not talking about lung cancer or anything like that. We're just
Right.
talking about like price per kilowatt hour.
the biggest thing we could do to shift to more renewables is to build out better transmission infrastructure across the U.S. So if we could connect East Coast with West Coast, the amount of available sun during the day would be bigger. And then the wind tends to blow in the morning and the evening. So you could have a really highly connected grid, similar to what's happening over in Europe, where it's like more connected. That could bring us to, I think, 90% penetration of renewables within a human lifetime. But we don't build that many transmission lines in the United States. There's a lot of blockers to doing that.
Yeah, it is kind of weird that there is all that trouble. And especially with Texas, like they don't want to have any of that West Coast or East Coast electricity, which I think makes their grid less resilient because they can't borrow from one place or another. They have to have everything
Yeah.
coming from there at the same time.
In ERCOT, yeah.
Yeah, and it's just like electricity's better when you can share it with the
Yeah.
further away, the better,
Yeah.
you know?
There are a few links that ERCOT has, but there's regulation saying they can't do it with AC power. So there's actually AC to DC go over the imaginary ERCOT boundary and then back to AC. So they do have some DC links to
I guess
other
too,
grids.
that would be a way to match the frequency, probably.
It's just because ERCOT has some stipulation that says that they're their own grid.
Oh, so they can't have any other AC coming from another over the border.
Yeah.
Yeah. What about
Yeah.
to Mexico? Do they count that?
I don't think they share power with
Yeah.
Mexico.
Because of like Tex-Mex, you know, that's good food and all that kind of
Yeah,
stuff.
Tex-Mex power, that works.
Yeah. But yeah, I mean, it just makes economic sense. Like you can only be stubborn for so long when the money makes it so much more worthwhile to just have a wire going across a border. It's going to eventually happen, I think. You know,
Yeah.
just like,
I mean, it's pretty interesting how much penetration of solar and wind there is in Texas. And California has historically been number one until late last year or early this year. Texas has more solar on their grid than California.
yeah, that's super awesome. And California does have a ton. And I can remember it wasn't too long ago, 10 years ago or something like that, we were going like, why don't they put solar in Texas? It's a sunny, perfect place and all that. And it was just like, they weren't doing it. It wasn't on the top list of places where solar's done. And now it's even beaten California. So
Yeah. The rate of installations in Texas is significantly faster paced than it is in California.
and that's all because of that job. But would you say 820
I mean,
megawatts?
that's not just because of that job, like that job's...
I'm trying to give you credit.
Oh. Thank you. The interconnection queues in California are about 7 years is the average. So 7 to 10 years. If you take a project, submit it to PG&E or SoCal Edison, it's 7 to 10 years to bring
in
it.
Such a fast-growing industry, that's stupid.
For utility scale, yeah.
That's like ridiculous.
Takes forever.
Yeah, so like who's behind that? Is it some Rockefeller and the oil company?
Like why it's like that, I'm not sure.
It's just because we have too much bureaucracy, I guess. Like what is it in Texas?
It's the national average is like 2.5 to 3 years.
So it's like California is like double or triple.
Double.
And then what about, do you know what Texas is?
Texas is probably like 2.5, 3 years, yeah.
Oh, so more like national average. And then what do you think about the Gobi Desert in China? Like 5 minutes?
Yeah. In China, it's not unheard of for them to build wind and solar before the grid's even there. I've seen and read stories about wind farms that have gotten built and there's nowhere to put the power because that's not there yet.
So that's economically interesting.
Yeah.
But that's at least as good that they're building it, and then I guess they're just a little behind on the transmission, maybe we could say.
And then to wrap it back to what we were talking about earlier with grid forming inverters, there's a new crop of mini grids and microgrids that are popping up in areas that don't have power, where there's no grid, and then you can power a whole community of houses, which I think is pretty interesting.
Great. Awesome. And I was just thinking too about the Texas thing where you said ERCOT, and I guess that's who operates the grid in Texas, right?
Yeah.
And Texas has their own grid and for special rules and all that kind of stuff. But if they could bring DC across the border, maybe that's kind of the way of the future anyway, is having this HVDC, high voltage DC, like megavolt type of stuff.
Yeah.
Did you know that with a megavolt that you can carry a megawatt with 1 amp? So you could use like a number 16 wire for a megawatt?
1 million volts.
Yeah.
A megawatt with 1 amp. So that matches.
Yeah. So then you could use a number 16 wire for a megawatt. Probably for 3 megawatts, 4 megawatts, no problem. Because they're just like 4 megawatts is 4 amps. Why not?
Yeah. I mean, one thing that would come in is you're going to seg that between 2 poles and yeah,
it's not like somebody's really going to do that, and you would still upsize the wire a little bit just because you'd be like, it's so cheap. Get rid of some voltage drop and make an extra $1 million or something like that.
Then, because the potential is really high, you would need to be really high in the air and have really big insulators away from that structure. You might want to hold it up by helicopters.
So then the big deal with why they want to do high voltage DC is with alternating current, as the conductor gets bigger, you get this thing called the skin effect, and the current likes to go around the outer portion of the wire. So that's one of the reasons why Paul was talking about multiple parallel connectors. And so if you're doing DC, you wouldn't have those benefits of wanting to use multiple parallel conductors. So you could just use one, which would be a benefit. And you could use the center of that big, thick wire. What's the biggest wire that you use?
The biggest underground wire that I use is 1,500 kc mils, so 1,500 kc mil.
That's like way beyond AWG.
Yeah.
And so a circular mill is the cross-sectional area of a circle with a diameter of 1,000th of an inch, which is kind of like the weirdest American way of doing things ever. And so you're talking about thousands of circular mills. So I don't know, go calculate that. It's your homework assignment. Do some pi.
American wire gauge, the smaller wire, like 30 gauge wire, is really thin. And then as you go down, you get bigger in gauge. So 8 gauge is what we use for PV, 8 or 10. And then you keep coming down and you get to 1 and you're like at the end of that. So then we still want to go bigger with our cable. So then we invented 0 gauge and still want to go bigger. So then we have 2 zeros and that's double the size. And then like, well, let's do 3 zeros. And then it's like, well, let's do 4 zeros, and then somebody finally said, like,
they call it 4-aught.
Yeah, we have a nickname for it because you don't say 0, wire. And then somebody finally said we need to come up with a different system. So you do kc mil, which is thousands of circular mills, and then the numbers go up, which makes sense.
Yeah, and then those Europeans and the rest of the world, they just do cross-sectional area in square millimeters. So that's too easy.
There's a transfer.
It's not good for preventing Alzheimer's and doing brain exercises by just doing something so easy as the metric system. And so another thing that you did mention is you said duct banks, right? Like duct tape?
Yeah.
Duct banks?
Yep.
Like the duck curve? No, I'm just joking around, but like maybe you can explain what a duct bank is.
If you have multiple conductors that are running parallel to each other and need to connect to a substation or a switch gear, you want to study the mutual heating there, and you can put them in a bank not one where you deposit your money. It can be concrete where there's spacers between each one of the conductors, and they just call it a duct bank. And you can study the different aspects of it.
So is it like a duct then?
Yeah, it's generally the cable's in conduit.
So explain the duct.
You can just think of it as conduit.
So how big?
You could do a small duct bank with,
How big's a conduit?
1/0 cable.
Or like the conduit itself that the cable's going in? Is
If
it like
I would-
inches across? Or?
The smallest duct bank that I would ever engineer would have 3 medium voltage cables in it, and it would probably be around 5-inch diameter up to 8-inch diameter.
And what kind of conduit is it?
That would be PVC conduit, or
So-
it could be HDPE, high density polyethylene.
So some sort of like plastic type of conduit. And what would the diameter be?
So let's say 5 inches,
So 5 inch. What's a big one?
8 inches.
5 to 8 inches, something
Yeah.
like that. Okay, so a duct bank being some sort of plastic circular conduit that's about 5 to 8 inches that you're putting medium voltage cables into.
A collection of those.
A collection of them, like
yeah,
multiple.
Yeah, like 6 of them or 8
6
of
of
them
them.
together.
Okay, and then they're just buried into earth with some
Yeah.
sand on them or something.
Yeah.
Okay, and we're gonna-
Sand, or you could encase it in concrete.
or encased in concrete. Cool. So we're going to make a class and we're going to look at some of this stuff.
Yeah.
So that'll be super, super awesome.
In my world, I try to stay away from duct banks because there's a lot of labor that's involved in getting it all into this location, and then extra material, so the costs will go up. In cities, you will find duct banks in like underneath a stadium.
Do they have them so you can add extra conductors later?
Yeah, and you
stuff
can
like-
fix it because the cable doesn't last forever. It's got a 30-year
Do you ever have, like, you're
lifetime.
talking about circular duct banks? Is there ever like rectangular or anything like that?
For cable pulling, I think it's almost always circular. I don't know about it. Anything that would be square.
Okay. Let's see. So some other things too that I just wanted to mention here
Yep.
is we talk about NorCal Solar. So-
NorCal Solar.
Woo! So Paul and I are on the board of NorCal Solar, and myself and Paul and our good friend Saad Yosefi, we're like the 3 power players on the resurrection of NorCal Solar. We just
Right.
had our 50th birthday party, and Paul was instrumental behind putting together the 50th birthday party. We had it during Climate Week, and we had it at Port Labs, and that's like a workspace in Oakland where
Right.
Paul works. We had lots of speakers. Do you want to mention a couple of the speakers because you were more behind organizing them?
Yeah, we had Danny Kennedy from New Energy Nexus, Will and Alba from Climatize, Jenya from Nevados, which is a tracker company, and we had Luis from EDPR, a renewable energy company. We had a presentation from, we'll just say, students over at Stanford University, which was pretty exciting, and quite a few other people that were there. We did both 5-minute talks and 3-minute talks. There's a recap of it up on the NorCal Solar LinkedIn page, and it was a resounding success.
Yeah.
And it was pretty cool to be a part of San Francisco Climate Week and have a 50-year birthday party celebration. Sean brought some cake, celebrated NorCal's 50-year and Bill Brooks's birthday, and Sean bought blue cake. So everybody that had cake, they had blue teeth, and you could look around the room and everybody had Smurf teeth.
I don't even think I even requested a particular color. I was just like, make me a cake, quick. Yeah, so that was super awesome. We did it on April 26th, which was Bill Brooks's real birthday. It was also the 10-year anniversary of almost the day that I got wiped out in a sailing accident. But here I am. I'm still alive, I think, unless
Still
this is some
sailing.
different dimension. We went sailing that day too. It was a lot of fun. So Paul Subzak is the Chief Strategy Officer of NorCal Solar. So that's pretty cool. 50-year-old organization. So that's super awesome. So thank you so much for being so instrumental in making that happen. So it wouldn't have happened without you.
Likewise.
Yeah, NorCal Solar is a chapter of the American Solar Energy Society, and also 2024 is the 70th anniversary of American Solar Energy Society and the International Solar Energy Society. And I recommend everybody to get involved with an ACES chapter. So if you're not in Northern California, there's a chapter that encompasses where you are, and if they're not active, be the one that makes it active. Become the chief strategy officer or the president or something like
Yeah,
that.
host an event. We've done big events with presenters, or we've also done small socials at a local bar, and people come, and some people have brought in different panels and stuff that they're working on, and both events are great in their own way.
Yep, great. And then we had a number of past presidents show up, including Claudia Wentworth, Elaine Hebert, and Pete Shoemaker. And I'm the current president. And Claudia Wentworth, who co-founded Quick Mount PV with Stuart Wentworth. Claudia Wentworth said that we tied for the biggest ever North.
Tied? I thought we won.
Yeah. Well, isn't that tied for number one?
Okay.
Maybe, she was just trying to make herself feel good because she was the president at that time.
But she deserves it.
And so, and she's an awesome person, still staying active in the solar industry even after selling Quick Mount PV. And also, I was just doing some recordings with Johan Alfson in San Diego a couple of days ago, and he is doing things for my NABCET PV Associate Boot Camp, and he worked for Claudia Wentworth at Quick Mount PV and other things too. So good. And do you want to also just tell people like what you do, give yourself an outroduction?
Yeah, so my current role is the Senior Engineering Manager at Conductor Power, which is an EPC. EPC means Engineer, Procure, Construct, and we build energy infrastructure across the United States, primarily solar, battery energy, substations is where the majority of our work is.
Cool, man.
And we operate across the U.S., generally in the Central Corridor, and we'd love to build your next project.
Yeah, so give Paul a call. You can find him. He's very active on LinkedIn, and there's not too many people that spell their last name Subzak.
Yeah.
So it's Paul Subzak, and I'm Sean White, and thanks for listening to Sean White's Solar and Energy Storage Podcast. To learn more, go to SolarSean.com, and you can find me there, and eventually you're going to be able to find the class where Paul and I shrink ourselves and go inside of some duck banks.
High five!
Woo!